Arakawa will continue with the second lecture on W algebras.
Okay, so last time I explained that the solid slice can be obtained by Hamiltonian reduction, where mu is a momentum up from product of G star and some orbit of G positive to the dual of Lie algebra of G positive. And any question about last time? It's okay. So, I want to describe this Hamiltonian reduction more algebraically in order to upgrade the definition to the vertex algebra setting. So I first explain classical BRST reduction. So I fix maybe homogeneous basis of G positive. So homogeneous means homogeneous with respect to this grading. And I write the corresponding structure constant as Cij k. Then first I introduce classical Clifford algebra. So this is a Poisson superalgebra. As a vector space, this is just a tensor product of Grassmann algebra of G positive star and Grassmann algebra of G positive. And then there exists a unique Poisson super algebra structure such that we have natural embedding of Grassmann algebra of G star to this vector space, which sends a generator xi star to some. So I write the image of map. So maybe I write xi star a dual basis, a basis of G, dual of G star, dual of G positive. And so this, and we have also embedding from Grassmann algebra of G positive to this one. So this is a definition. So these are embedding of Poisson superalgebras, where these Grassmann algebra So this is naturally superalgebra, where generator has odd degree, and we view this as a trivial half is equipped with a trivial zero Poisson bracket. So Poisson bracket between these and between these are just zero. And I just have to specify Poisson bracket between these generators. And this I specify as delta ig. So this is super bracket. So super Poisson algebra means it's a least super algebra with respect to this bracket. And this is the odd generator. And then I consider, so I want to start with function on G star times this orbit, which is a tensor product of function on each affine spaces. So in fact, these both are polynomial ring, as we have seen yesterday. And then I tensor with this Poisson superalgebra. So this is naturally Poisson superalgebra. So I require these all elements all commute, all Poisson commutes. And then I give grading. So this is going to be homological grading as follows. So Shiva I is Shi of Okai tensor. So this is sum of lambda I G positive star tensor lambda G positive J, where I minus J equals to N. Sorry. So maybe this is N. So I assign degree of psi I star to be 1 and a degree of psi I to be minus 1 and degree of other generator at 0. So this is so this gives a G grading. And then I define element Q bar to be the following element. So I sum one tensor mu 2 star xi tensor psi star minus 1 tensor minus half Cij k psi star psi j star psi k, where I is from 1 to dimension of G positive, and here I, J, K k is from 1 to dimension of G positive. So this is element of C bar 1 because this one has degree 1 and this has degree 1, this has degree minus 1. So in total, all elements has degree 1. And then you can show either by computing or conceptually that the Poisson super bracket of Q equals to 0. And because Q bar is odd element, this implies that the adjoint of Q bar a square equals to 0, where add Q bar X is of course Poisson bracket with Q. So this is because it's, so we want to show that this kind of bracket is 0, but then this is equals to, by using super Jacobi identity, because both of these elements are 0, we have minus sign here, and then get what? Q bar A. And because this is 0, we find that this element must be 0. So, and this one, because this one has degree 1, this has a structure of a complex. And in fact, this is, because this is defined by adjoint, the adjoint action is compatible with Poisson algebra structure. So this is a differential graded Poisson algebra. So in particular, the corresponding cohomology, which is defined by kernel divided by image, has a structure of Poisson superalgebra, or graded Poisson superalgebra. So multiplication Poisson bracket is will define in the Poisson cohomology class. Then theorem says so we have first for this cohomology vanish for non-zero I, and this is isomorphic. H0 is isomorphic to the Srodowitz function, the Srodowitz slice as Poisson algebra. So let me explain the proof. So this complex is by definition bi-graded. Maybe Cn, Cij, where C bar ij is C G star tensor, maybe C bar ij tensor lambda I of the positive star and lambda minus j of the positive. So I put the minus sign for j because this has degree minus 1. So I is non-negative and j is non-positive. So C bar n is the sum of Cij with I plus j equals to n. Now, if you look at how this adjoint action of this operator acts, you find that this has two components, d1 plus d2, where d1 sends C bar ij to C bar I plus 1j, and d2 sends C bar ij to C bar I j plus 1. So Q has two components, I and j, and one goes this way and one goes this way. And the condition that its square equals to 0 means that all of these elements are 0. So this means that the d1 square equals to 0 equals to d2 square, and d1, d2 plus d2, d1 equals to 0. So we conclude that this complex is a total complex of double complex. So if you have a double complex, you find a spectral sequence. So there exists a spectral sequence, which converges to this cohomology, such that the first term is a cohomology with respect to d1. And E2 is a cohomology of E1 with respect to D2. Because D1 and D2 anti-commutes, this cohomology is well defined. And if you look what D1 is, then you find that we find this E1 term, which is cohomology with respect to D1, is the algebra homology or Koszul homology with respect to the action of G positive that appeared yesterday. So this is the same as Kosuzuru homology I talked last time. And because this is polynomial algebra, the action by multiplication is free. So we have a vanishing of homology. So this is delta Q0, and we get a function on the level set, as I explained yesterday. And then if you look the spectral sequence in the second page, this cohomology. So now we get just C of function on the sorry. I need Grassmann algebra. Did I forgot to put star here. And so you find this cohomology is nothing but Lie algebra cohomology with respect to the adjoint action of G positive on this level set. And because this is isomorphic, a tensor product of this one and this one by Gahn-Ginsburg theorem, where G acts only this part. So this is the same as HP of Lie G positive with coefficient in the coordinate ring of the group. And because G positive is unipotent, it's known that this Lie algebra cohomology is the same as algebraic drum cohomology. And because G positive is affine, we have also a vanishing of cohomology. And we get just function on the Srodoi slice. Here I use the fact that the G positive is unipotent. Yeah. Algebraic drum cohomology of G positive. No. It's 0. Something wrong? So this is Lie algebra homology, and this is Lie algebra cohomology. I forgot. Thank you. Was it your question? So as I told you, so Hamiltonian reduction is a mixture of homology and cohomology. And so BRST complex does this at once. And you see this by looking at the corresponding spectral sequence. So, in general,
they are actually homology of forms that are tangent to this width that you have in this layers. So what you're saying here is that the specific case of G is the algebra where is higher for all the dimensions.
yeah.
So the characteristic of this the algebra that you are
So I'm using the fact G positive is unipotent. It's isomorphic to affine space. So in general, this part remains, but zeros on zeros cohomology we obtain this because when G is connected. So we have, so this means spectral sequence collapses at E2 equals E infinity and get the desired isomorphism. N add Q bar delta N0 C. All right. So this is very algebraic description of Hamiltonian reduction. So we can use this construction to do similar thing for the vertex algebra. So now I want to talk about this. So chiralization of this construction. So what I want to do? So I want to, so this is same split as the correspondence when I explain about 4D2D duality. So I want to replace Poisson variety with a vertex algebra whose associated scheme is isomorphic to this one. So I want, so natural replace, natural chiralization for G star is the universal affine vertex algebra. Here, K acts as K and other elements act 0. So this is universal affine vertex algebra. And this indeed gives the G star when you take associated scheme. And what else we have to consider? We had G positive star. So this is very easy. We just replace this by the vertex subalgebra generated by elements from G positive. Here I'm identifying G as a subspace of VKG by sending X to X, T, inverse 0. And so this indeed gives back the G positive by taking associate scheme. I don't put K because this does not have any level dependence. And then we had a momentum map. So what was momentum map? From G star to G positive star. So this was just a restriction. So I replace this by the natural embedding from VG positive to VKG. And this indeed recover this one by taking, so this induces, this recovers this morphism by, if you consider a morphism between associated schemes. So what else we had? We had orbit, or chi, which was isomorphic to the symplectic vector space. So I replace this by, so maybe I write V or chi. So this is a beta gamma system, or a wide vertex algebra associated with a symplectic vector space G half. So this is generated by phi I, which correspond to the basis of G half. And a lambda bracket is determined by the chi of xi, xj, where xi are a basis. So I'm using the same notation, but so this is a basis of G half. So this is it's just a free field vertex algebra. And then you find that you recover this one by taking associated scheme. So this lambda bracket comes from the fact that the function on chi was isomorphic to symmetric algebra of G half, where Poisson bracket was defined by this formula. So I just wrote this formula here. Then what is momentum map? So this should be a morphism from V of G positive to V of O chi. And this is defined as xi goes to something wrong. 0 if I is if xi belongs to G greater than 1, and xi goes to chi of xi if xi is an element of G 1. under phi I if xi belongs to G half. And you can easily check that this is a vertex algebra homomorphism. And you obtain, by taking associate scheme, you recover the morphism from V of OK, which is the same as OK, to so natural embedding of natural embedding, which was the momentum map for OK. Okay, so I think I have, no, I still have to explain one more thing. So I had also this classical Clifford algebra. So I just replace by what is called space of semi-infinite forms, or free fermions. Free fermions. So this is generated by odd generator, which is psi I. I'm sorry, I'm writing the same notation. I should have put the bar for the previous one. So I is from 1 to dimension of G positive, and the lambda bracket is just phi I lambda, phi j star equals delta ij, and the other bracket are 0. So this exactly corresponds to the super Poisson bracket of the classical Clifford algebra. And then if you take Zhu-Shitsu algebra, which is naturally defined for the super vertex algebra, you recover this classical Clifford algebra. Okay, so I have all ingredient. So I now can replace now I can consider this tensor product, VKG, which corresponds to CG star, and then V of OK, and then semi-infinite forms. And then I also have to define a differential. Actually, this is defined by the same formula. So Q is defined by xi tensor 1 plus 1 tensor mu 2 hat star xi tensor psi star minus 1 tensor 1 tensor Cijk psi star psi j star psi k. But this time I think as an element of vertex algebra. And then what you can show by computing or by conceptually that the lambda bracket of this element Q is 0. So this in particular means, because Q is odd, zero mode action, square of zero mode action is 0. So I'm expanding QG corresponding field as Qn G minus N. So again, we have a complex. Maybe I define to be C of VKG because I don't want to write each time. So the C of VKG, Q0, is cochain complex by the same cohomological grading as before. And actually, this Q0 is compatible with algebra structure of vertex algebra because of the reasoning I explained in the first week of the school. So this has a structure of differential graded vertex algebra. So in particular, cohomology is naturally a vertex superalgebra, a G-graded vertex superalgebra. So this is exactly the same story. And the theorem so this was first proved by Fagin and Frenkel for principal nilpotent element and for generic K, and then De Boer Tijin by for principal nilpotent element for type A, and then Frenkel Bensby for principal nilpotent element, and finally Katz and Wakimoto for all cases. That this cohomology, we have the cohomology vanishing again. So, we have only H0, which is a vertex algebra because we don't have any odd element. And this is defined to be the W algebra. So this is W algebra associated with G F at level K. So, as you have seen, everything was totally parallel to the classical setting. We just have to replace. We just have to consider chiralization of each one. And then we reach the definition of double algebra. Yeah, so this definition was found by Fagin and Frenkel for principal nilpotent element, and Katz and Rowan Wakimoto in general. Now, so you have this nice diagram, vertex algebra, Poisson vertex algebra, Poisson algebra. So I explain Poisson algebra setting, and then I explain vertex algebra setting. But if you have anything here, so this is kind of both of these, all these objects. So you have something here, you can obtain any corresponding objects in the everywhere. So let me explain compatibility of this construction to this diagram. So related BRST cohomology. So first for the Zudd-Sheets algebra, let me start with the Poisson algebra setting. Zudd-Sheets algebra of CKVG is just a tensor product of each of Zudd-Sheets algebra. So this one and this one, this. So this is C G star tensor C of Okai and classical preferred algebra. And so image of Zudd-Sheets algebra, if I denote by Q, we have an action of Poisson bracket. And so square of this equals to 0 because Q0 square equals to 0. So we can consider graded, differential graded Poisson algebra defined by AddQ. But this is identical to the complex I explained in the beginning. So this is identical to the complex BRST complex already appeared. So this is defined by the Q bar I explained in the Poisson setting. So you can do two things. First, you consider a Poisson Zudd-Sheets algebra BRST reduction, or you can consider cohomology of Zudd-Sheets algebra. What? So this is C R of V C VKG add of Q. And it's not trivial at all that this is the same, but for this one can show it's a theorem of Zezel and Katz that this are in fact the same. And this is nothing but the C2 algebra of WKGF. And this is isomorphic to the function on the Srodwy slice. So this means that the associated scheme of double algebra is the Srodwy slice at F. So may be. So what I have seen, we have seen. So I started with VKG, and I obtained WK, define double algebra by BRST reduction. So this is BRST. but you have, maybe I, so you have a function on G star and WKGF and a slot E slice. And the yellow line is a BRST reduction. And so this is arrow is C2 functor of taking C2 algebra. And this theorem says this diagram commutes. This is C2 algebra. So R. So this is BRST. And you can discuss compatibility with the Poisson vertex algebra version, because a group of CVKG is as unexplained naturally Poisson vertex superalgebra. And the Q0, image of Q0 acts as, so this square of Q0 equals to 0 on this associated graded, of course. Maybe I don't have to put bar, I'm not sure. So this is differential graded Poisson vertex algebra. So this is exactly the same. And then you can ask whether associated graded of H0 of C of VKG is the same as H0 of this differential graded Poisson algebra. So maybe I put N. So maybe I put N everywhere. Group of C of VKG. And one can show that this is indeed the same. So this is isomorphic. So this is delta N0, a group of WKGF. And this is a delta N0 of function on the Z of a slot is. So this isomorphism, the proof of this statement is exactly the same as Poisson setting by the reasoning I explained yesterday. So this means that the singular support of double algebra is exactly the infinite jet scheme of the slot slice. So here again, we have, so I should not, here I have a function on the jets. Maybe I should, so maybe I should have explained it more explicitly. But so this is written in terms of jets, and this statement is the same as BRST. Reduction of this one is the same as the jets of the slot slice. So we have commutative diagram here again, and here again, it is just taking zoo algebra. And then finally, you can talk about the Zoo's algebra, which is non-commutative version. So if you consider Zoo's algebra of H, how do I say? So Zoo's algebra of a complex we can let add image of Q act on this algebra naturally, because this is algebra. So if maybe, how do I say image of Q? So I identify Q with the image in Zoo's algebra. Then you can take, because this is an algebra, you can define adjoint. Then because Q0 square equals to 0, you find the adjoint of this equals to 0 so, as well. So you obtain this way differential graded algebra. And then you can ask again whether if you take Zoo's algebra of cohomology, or either you can take cohomology of Zoo's algebra and ask whether this is the same. And in fact, this is the same. So this is and the left-hand side is, of course, Zoo's delta in 0 of Zoo's algebra of double algebra. And the right-hand side is shown to be finite double algebra associated with G and F. So it's done. The real. Continue dissolve Helgani and cut. So again, diagram for the Zoo's algebra also commutes. So we conclude that everything commutes in this correspondence. So this is a very nice construction of a vertex algebra. Now you can ask whether vertex algebra obtained in this natural construction is a nice object or not. So for this, I now go into the representation theory of double algebra. But any questions so far? Yeah? Sorry?
From this construction, are we able to get information about COPs between the strong generators you mentioned?
Of course, it's a quantization of Poisson structure, so you know the leading term. But it's difficult to compute the whole structure. But in principle, it's possible to compute if you have a strong computer. Now, now I want to talk about representation theory. But as I explained, we don't really know the OPE of double algebra. So we cannot expect that we can study a representation theory of double algebra directly, because we don't know the commutational relation. So, but nice thing about this construction is that it constructs modules also automatically. So let me explain this. If M is a module of this universal affine vertex algebra, which is the same as a G hat module, smooth, maybe smooth, G hat module of level K, you can consider as the similar complex. So M tensor, so we replace VKG in the previous construction by M. Then this is naturally a module over C of VKG because this is a tensor product of VKG and V of Okai and this lambda semi-infinite G positive. So this one acts here and this one acts here and this one acts here. So this is naturally a module. And here is the element Q, whose square equals to 0. And because this is element here, it also acts keeping this relation. So we can consider corresponding complex which is complex, and this is complex, and if you can consider cohomology, this is a naturally module over H of CKG, which is a double algebra. So the action of here of this one on here induces the action of this one on here. So the action is well defined on the cohomology. So you have a functor from the category of smooth G hat module of level K to the category of module of a double algebra, which send M2 H0, maybe I should write this to be H dot ds. So this stands for Dirichlet-Sokolov reduction of M. So H0 of this cohomology. So get functor. it's easy to see that this is compatible with morphisms. So now you want to ask, so is this functor useful? So if this functor is useful, we can use what is known about the jihad module to study double algebras. So to get some idea with it's good or not, it's always good to what you can say about the most classical setting. So maybe I should explain refiltration for modules. So unexplained refiltration for vertex algebra. But you can define refiltration for module exactly in the same way. So if M is a vertex algebra, if V is a vertex algebra, and M is a V module, you can define filtration as following. So it's a span C of A1 minus N1 minus 1, AR minus NR minus R, M, where AI is an element of V and M is an element of A, and sum of NI is equal or greater than P. So again, you just count how many derivations you have. Then you find that the same properties that the refiltration has. So multiplication of FPV of n to FQn is in FP plus Q minus n minus 1 m for all n, and in fact this is inside Fp plus Q minus n, which is contained here if n is non-negative. So this is for n. And then you find that this GUR of M is a PVA module over a GUR of V. I don't want to explain what is PVA module, but you can easily guess. And this in particular implies you restrict this action to the first component, namely M over F1 M. So this is a Poisson module over RV. So what is Poisson module? So Poisson module is a module, it's a module, R module, as commutative algebra, also equipped with Lie algebra action of R. So R is a Lie algebra by Poisson bracket. So you can talk about a Lie algebra action of R, and these two actions are compatible. So compatible means, for example, the following formula holds. So if you write the algebra action by using a Poisson bracket, then we should have following identity. So this is multiplication, and R2 and R1, etc. So to get some idea what is Poisson module, this is, if I write as this, sorry. So when R is CG star, Poisson R module is the same as CG star module is the same as CG star module as commutative algebra equipped with a Lie algebra action of G, because Poisson structure coming from Lie algebra structure of G. So it's enough to define Lie algebra action of G. And such that the following formula holds. So if X is an element of G, so if I write, yeah, the same formula, sorry. So it's the same formula, maybe I don't have to write, but maybe it's okay. If is an element of CG star, and yeah, etc. So, but this formula looks quite familiar. So, if you consider the category of Poisson CG star module, you have a full subcategory consisting of modules on which the algebra action of G integrate to the action of group. And this category can be identified with a category of quasi-coherent sheaves, a G equivalent quasi-coherent sheaves on G, where F is sent to the global section. So similarly, if you consider Poisson vertex algebra modules over C of J infinity, G star you have full subcategory consisting of quasi-coherent sheaves G infinity G equivariant quasi-coherent sheaves on the arc space of G star. Now, let's go back to our setting. So CG star for some CG star module on which G action, D algebra action, integrates to the action of G.
Oh, so that's a condition that it integrates.
Yeah.
Okay. And do you want to have a condition on the Poisson side?
What do you mean Poisson?
So in the bottom line, do you want to have a condition that the G
Here?
yeah, so that the top level integrates the group, or
Yeah, so this is full subcategory. So this is the same as it's the same thing as this. What I wanted to say. Yeah, so M was VKG module. Then the complex is tensor product of these things. And then quotient by F1 space is the same as tensor product of quotient by F1 space. So this is tensor product of C of OK and classical Clifford algebra. And this is a module over Poisson module over R of C of VKG. So we have complex add of, so add means the algebra action of Q1. So this is Poisson. So if you, this is complex, and if you take corresponding cohomology, we have Poisson module over H0 of R C of VKG, which is Solodoi slice. But here you can put any. This can be any Poisson CG star module. So to define the action of R of CKG, you just need this is a Poisson module of a CG star. So you have a functor which sends Poisson CG star module to Poisson CSF module, which sends M to H0 of this complex. So M tensor C of OK, tensor Clifford algebra, and add of Q bar. So this is most. So this is the Poisson version of the Drinfeld-Sokolov reduction functor. So you can ask whether this functor is good. And if it's good, you can hope that the functor for the vertex algebra module can be also good. And the theorem by Losef and Ginzburg if you restrict this functor to the full subcategory consisting of quasi-coherent G-equivariant quasi-coherent sheaves on G star, so which is the same as Poisson CG star module on which the algebra action of G integrates the algebra action integrates to G, then we have a cohomology vanishing. So M tensor C OK tensor C L and Q bar. So this is delta I0 and C is F tensor C G star M. So this is a statement. So in particular, the functor which sends equivariant coherent sheaves, quasi-coherent sheaves to a Poisson CSF module, which so M2, this H0 CSF tensor C G star M is exact. So I don't have much time, so I don't explain the full proof, but I'm going to explain why this functor is exact and why this equivariant condition appears. So proof of exactness of so the key point which is known by Briscoe and Slodwy, that this Slodwy slice intersects G orbits let's say G orbits transversely at any point. So why this is useful? So this means that the action map from G times SF to G star, which sends GS to the action of add star G of S. So this is smooth because it induces a surjective map between tangent spaces. So this is in particular, this is in particular flat. And of course, flatness implies exactness. So the functor from the category of CG star modules, which maybe I identify with the category of quasi-coherent sheaves on G star to C of G times S, that sends M to C G tensor SF tensor C G star M. So this functor is exact. So now one can use the following trick. So proposition, if M is a G equivalent, then this space is isomorphic to this one. So you can just put CG out from the bracket. So this is easy to see when M is a coordinate ring of G affine G scheme. So the statement says so in this case, statement is equivalent to the statement that G times Fs times G star fiber product over G star with X is isomorphic to G times fiber product over G star of SF and X. And this isomorphism is easy to find. So this is a set which satisfies this condition. So you can just send G to S and G inverse X. Oh, sorry. Thank you. So this is a case for the when M is a function on the of G scheme, but the corresponding isomorphism of coordinate ring is obtained by using co-module structure of this ring. So if M has a G action, you always have co-module structure. So using co-module structure of we get the isomorphism in general. So if you look at this formula, so you can, when you restrict to this functor to the coherent, quasi-coherent, G-equivalent coherent sheaves, so this is the same as CG tensor CSF, tensor CG star M. So exactness of this is equivalent to the exactness of functor without this one. So exactness of star is equivalent to the exactness of quasi. Okay, so my time is over. So I stop here for today and I explain the analogous statement for the vertex algebra setting tomorrow.